Okay, let's take a look at the Calculating Half-Life of Radioactive Isotopes worksheet that we have been working on. We've done all of the ones so far where we know, again, let me just write down the formula before I do this so I can refer to it. We know it's A, the ending amount, equals A sub 0, the initial amount, times 1/2 T is the amount of time that is elapsing, and then H is the half-life. And again, this is an exponent. Sorry, it looks like it's multiplied by, but it's an exponent. So we've done all the ones on this worksheet where we know the initial amount, we know how much time has elapsed, and we know what the half-life is. But there are other variations of that. In some of the problems, we might know the ending amount but not the initial amount, or we might know the ending amount but not the time, or the ending amount but not the half-life. And so what we're going to look at is some more problems on here that are of that other format. All right, so there's really two different types that are left. The type that's like in problem 2, and then the type that's in problem 4. And again, I believe that there are, let's see, 1, 2, 3, 4, 5 problems left. So 3 of them are of this type, and there are 2 of this type. Okay, so let's take a look at problem number 2. A 50-gram sample of, I don't know what that stands for, 16N, nitrogen 16, maybe decays to 12.5 grams in 14.4 seconds. What is its half-life? Right, so as we go through here, we're trying to identify whether we have the the ending amount, the initial amount, the time that's elapsed, or the half-life. So again, as we go through, a 50-gram sample of this material, decays to 12.5 grams in 14.4 seconds. What is its half-life? So hopefully it's easy to see here that we're looking for H. All right, so we're going to write here H. We don't know what it is because it tells us that that's what we're looking for. All right, so then we want to see what of the other 3 do we know? Actually, we have to know all of them. So what are they? So as we go through here, a 50-gram sample decays to 12.5 grams. Which is the initial and which is the ending amount? Hopefully when you see that it says it decays to this, that you realize that's the ending amount. All right, so that would mean that our initial amount, A sub 0, is 50, and our ending amount, A, is 12.5. And then the only other number in here is in time, which is fortunate because that is what that's the only other variable we haven't listed. So the time is 14.4 seconds. Okay, so I'm going to start by writing the formula out. A equals A sub 0 times 1/2 to the T over H. And then I'm just going to fill everything in. So 12.5 equals 50 times 1/2 to the 14.4 over H. All right, so far it's not any different from the other problems in terms of steps that we go through to read the problem, to write down what we know, to fill that in the formula. What's going to be a little bit different now is how we solve it. So again, we just had spent some time recently talking about exponentials and how to solve exponentials. And while we never had any bases that were fractions like this, we ran into problems just like this, right? And so what we did with those problems is we said, okay, this right here, this exponential is where our variable is. Right now, that's the H is the only thing we don't know. So anytime we run into problems in algebra where we might have something like 12.5 equals 50 times x, then we would say, well, what do we have to do to solve it? We need to remove anything that's not with that variable. So for starters, we're going to have to remove that 50. And so what we're going to do is we're going to take it and we're going to divide both sides by 12.5. All right, so I'm going to get 12.5 over 50 equals 1/2 to the 14.4 over H. Again, sorry that this is looking like multiplication. It's not. It's really, maybe I should make this longer. Okay. Now, again, there's the question of when do we convert this to a decimal? I'm going to wait, right? And then you also might say, okay, well, we just did that sheet where we would take and rewrite things in logarithmic form. You could do that here, but I'm going to suggest that we try a different strategy for this. And that is that we take the log of both sides. The reason I'm suggesting that is because, again, here we have the variable sitting up high. Again, this is kind of like street level right here. And the exponent where the variable is sitting up in this position. And we want it to be down on street level. We want h to be right here so we can say h equals something. And one way to do that, a very common way to do that, is to take log of both sides. Because if you remember, we have this power rule in logarithms that says if I have log base b of m to the nth power, that exponent will just come down in the front as a coefficient, and I will have n times log base b of m. So I don't have a log right here, I just have an exponential, but if I take log of both sides, then I will be able to apply this rule. So here's what I'm going to do. I'm going to use log base 10, only because I can do that on my calculator then. So I'm going to have log base 10 of 12.5 over 50 equals log base 10 of 1/2 to the 14.4 over t. All right, this right here is a number. All right, when I plug that into my calculator, it's going to spit a number out of that. Even though we see letters in here, we should not think that this is a variable of any sort. This is a number. All right, so we're just going to leave that alone for just a second. We're going to come over here and recall what I just said about this, that when I have log of something to an exponent, I can use the power rule and bring that down front. So I'm just going to leave this log of 12.5 over 50 equals, and then I'm going to write that as 14.4 over, oops, sorry, that was a typo. This should say h. 14.4 over h times log of 1/2. All right, so I took that exponent and I brought it down the front, so 14.4 over h times log of 1/2. Right? Again, just as I said, this is a number right here. This is also a number right here. Log of 1/2 is just a number. Right? And again, when we have a number equals something that has a variable in it times just another number, our strategy is to get things away from this where the variable is. So I'm going to divide both sides by log of 1/2. Right? So I'm going to get log of 12.5 over 50 divided by log of 1/2. Now remember, don't try and condense anything. This is log of the top divided by that other number, which is the log of the 1/2, equals 14.4 over h. All right. Now let's, sorry, I'm going to have to move down into this next spot. Let me write that again. Log of 12.5 over 50 over log of 1/2 equals 14.4 times h. Now I'd say let's try and figure out what that is. All right, so grab your calculators. And I'm going to do log of 12.5 divided by, whoops, divided by 50 divided by log, you can write 1 divided by 2, I'm just going to do 0.5. Dang, 2. All right, so this becomes 2, and I'm going to write it as 2 over 1 equals 14.4 over h. All right, as I do that, then I can cross multiply, and I get 14.4 equals 2h, and then I divide by 2, and I end up with H equals 7.2. And we need to give the units here, so let's go back up to the problem. The units in our time were measured in seconds, and so the units in our half-life have to be the same thing. So this has to be seconds. All right, now let's talk about why this condenses or simplifies into 2. So let's go back here. We were just saying this is a number right here, but this is the same thing as 1/4. If I multiply 12.5 times 4, I get 50. Actually, if I multiply 12.5 times 2, I get 25, and then another 2 times would be times 4 would be 50, so that it ends up being log of 1/4 over log of 1/2. Okay, now let's think about this. This it should remind you of your work and change of base formulas, that if I end up with log of something in one base over log of something in the same base, that really it was the same thing as log of the top, 1/4, in this base. All right? So if I were to expand this, I would get this right here. All right? Well, then this is asking the question, 1/2 to what power is 1/4? And that would be 2. That's why we ended up getting 2 right there. You would not necessarily recognize that as you're doing the problem, but that is the reason that we get 2 right there, instead of some very heavily decimaled number like we have been looking at before. Okay, this I would say is the harder of the 2 types, because we've got this extra step at the end because the variable's in the denominator. But this one is going to be very similar in the strategy. There's going to be one difference, and that is that we're not looking for H this time. All right, so then let's go and take a look at number 4, and let's read through it. What is the half-life of, I'm embarrassed to say, I don't know how to read that. TC of 99, I don't know. Sorry, I'm not a chemist. If a 500-gram sample decays to 62.5 grams in 639,000 years. Right? So as we go through, it's asking now, what is the half-life? Darn it, this was the same type. Okay, I'm going to change my mind. This is the same type. Let's look for another one that's different. Okay, let's look at number 8. So this is different. This should be of this type. I think I just did it the wrong symbol. How many minutes? Okay, so these 3 are all of the same type, 8, 12, and 13. All right, so let's look at problem number 8. A 2.5 gram sample of an isotope of strontium-90 was formed by a 1960 explosion of an atomic bomb at Johnson Island in the Pacific test site. The half-life of strontium-90 is 28 years. In what year or how long will it only be 0.625 grams of this strontium-90 remaining? All right, so it started in 1960. That's when the explosion occurred. And so they're asking in what year will it be, but in order to figure out what year, we have to figure out what time has elapsed, right? So what we're looking for in this problem is T. We don't know what it is. I'm actually going to write it above here so I have more space in here. So T, we don't know. That's what we're looking for. So that means that we must know everything else. So we're going to know the initial amount, we're going to know the ending amount, and we're going to know the half-life of it. All right? So again, let's read through to find out what we can. A 2.5 gram sample of an isotope of strontium-90 was formed in a 1960 explosion of an atomic bomb. The half-life of strontium is 28 years. And in what year will only 0.625 grams remain, right? So in this case, we would say, well, it's very explicit here. The half-life of strontium-90 is 28 years. So that is going to be our H value. And then again, with decay, the larger one is the initial amount and the smaller one is the ending amount, because we're letting things decay, get smaller. So our initial amount is going to be 2.5 grams and our ending amount is going to be 0.625 grams. Okay, let's write the equation. Ending amount equals initial amount times 1/2 to the T over H. All right, and let's fill in what we know. The ending amount is 0.625 equals the initial amount, which is 2.5 times 1/2 to the T, which we don't know, over H, which is 28. Okay, so just as before, this is where our variable is right here, and so we're trying to get everything over to the other side. Right? So when we do that, we end up with 0.625 over 2.5 equals 1/2 to the T over 28. All right, and again, just as before, if we would like to get this variable down to this regular level right here, so we can write T equals something, then we need to get it down. All right, and to do that, we're going to take log of both sides. So log of 0.625 over 2.5 equals log of 1/2 to the T over 28. All right, let's go up here. Now that we have log of this, I can use the power rule, which says that if I have log of a base to a power, I can bring the power down as a coefficient. So now we're going to have log of 0.625 over 2.5 equals T over 28 times log of 1/2. Again, it's very easy to be stressed out by these two because they have letters in them and we think of them as variables, but log of 0.625 over 2.5 is a number. Log of 1/2 is a number. So I need to get this variable by itself, and so I'm going to divide both sides by log of 1/2. So I'm going to end up with log of 0.625 over 0.25 divided by log of 1/2 equals T over 28. All right, now let me use my calculator to figure this out. Oops. All right, so I end up with log .625 divided by 2.5 over log, this time I'll do 1 divided by 2, it doesn't really make a difference, and I get 2. Again, they're giving us nice numbers. They don't usually work out this way. We probably could solve this another way, but I really want you to know this strategy of taking logs of both sides. So anyway, we end up getting 2 equals T over 28. All right, we don't need to cross multiply here. All we need to do is get rid of this 28 that T is being divided by. So I'm just going to multiply both sides by 28. All right, so I end up with 56 equals T. Again, we need to find the time in order to answer their real question, which is when or in what year will only 0.625 be left. So we know that T is 56. In other words, 56 years has elapsed from 1960, which means we want to add 1960 onto it. And we would end up with 610, we would say in 2016. So in 2016, only 0.625 grams will be left. Okay. So I'm going to ask you to try a couple of these on your own. You might want to go back and watch the videos again, because I think just watching it once is not necessarily enough. So again, sorry about